Ja, som sagt, i dag har vi 3 talks. Jeg starter med Mikkel og Vemund. Og så tar vi en liten pause innimellom. Vi kan ta litt drikke, gå på do. Ja, og så i tillegg så har vi denne fine boksen, som er en mikrofon, og den kan vi bruke til å stille spørsmål. Så på slutten av talken så kan vi kaste den rundt. Det er veldig smart, så den skrur seg av det man kaster den, og så kan man stille spørsmål til mikrofonen. Så får også de som sitter på streamen med seg spørsmålene. Ja, har du noe glemt?
Nei, jeg tenker vi kan starte.
Ja, da er vi good.
Ser vi?
Ja, det blir godt jo.
Hallo alle sammen. Jeg heter Mikkel Algren og jobber i Knowit som konsulent.
Yes, jeg heter Vemund Rudsagen og jobber også i Knowit som manager i Knowit Insight.
Og det vi skal snakke med dere om i dag er innovasjon. Fordi hvis det er en ting man observerer i dagens samfunn, så er det at hastigheten som ting utvikler seg på i samfunnet egentlig bare akselererer og akselererer. Noe som selvfølgelig for bedrifters del betyr at de må innovere desto raskere for i det hele tatt klare å holde seg konkurransedyktige. Utfordringen er at innovasjon er vanskelig, og suksessratene er enormt lave. Men det vi skal snakke med dere om i dag er at det er nye rammeverk som tar i bruk teknologi for å kunne gjøre innovasjon mer mer forutsigbart. Faktisk hele 5 ganger så forutsigbart. Så dette er et jobbsentrisk, vi skal komme litt tilbake til hva det er, rammeverk som tar i bruk kunstig intelligens for å bedre kunne imøtekomme kundebehov. Og slik vi tar og inndeler dette her, er at vi først tar og forteller dere om hvordan dette rammeverket fungerer. Deretter tar vi og ser hvordan man kan ta og gjøre nettopp denne imøtekomme kunders behov best mulig. Da gjennom faktisk clusteranalyse, som er selvfølgelig en konvensjonell AI-metodikk. Og jeg tror det som er spennende for dere i den settingen nettopp hvordan dette er anvendt i en såpass praktisk setting. Og senere vise hvordan vi faktisk har gjennomført dette rammeverket på en pilot som vi har kjørt på kaffemaskinen, hvor vi kan se for oss at det er en tenkt kaffemaskinprodusent som ønsker å bedre tilpasse sine produkter og tjenester til sine kunder. Eventuelt personer på Knowit-kontorlandskapet.
Takk skal du ha. Yes. Og jeg skal snakke litt om den øverste av disse 2 bolkene. For i bunnen av dette rammeverket vi nå er i gang med å utarbeide for våre kunder, så ligger noe som heter Jobs to be done, som Mikkel var inne på. Og så er det noen smartinger fra statene, et selskap som heter Strategin, med Anthony Ulvik i spissen, som har utviklet Outcome-driven innovation. Og det er det jeg skal hoppe litt på, rent sånn fra forretningssiden, før Mikkel tar seg av hvordan. Yes. I bunn og grunn så ligger, eller i bunn for Jobs to be done-metodikken, så ligger en tanke om at alle produkter og tjenester som folk benytter seg av, de ansettes for å få en jobb gjort. Veldig kjent eksempel er Milkshake og Clayton Christensens studie av det, for de som kjenner til det. Og så er det viktig å ha med oss at dette er noe som tvinger folk til å bli, eller de som utøver disse studiene, til å bli mer behovssentriske, se på problemene kunden har, mer enn løsningene og produktet. Og det kommer jeg også litt tilbake til hvorfor det. Men det sitatet nederst her om at folk strengt talt trenger hull i veggen, og kanskje i ytterste konsekvens den hyllen de eventuelt skal henge opp, mer enn akkurat drillen, er også typisk veldig sånn toneangivende, eller går igjen da. Så er det sånn at behov, det har alle bedrifter en formening om at de må vite hva er for noe, men det er få som faktisk har en omforent take på hva et behov og hva et kundebehov Noen mener det ene, noen mener det andre. Og i tillegg, av ulike årsaker, så endrer ting seg. Behov, avhengig av hvordan man definerer det, kan endre seg over tid, spesielt løsningssiden av dette, med teknologisk utvikling, fra sted til sted og så videre. Vi har lyst til å poengtere at et behov det må være stabilt over tid for at man skal kunne støtte seg til å bruke det som noe verdifullt i innsiktssammenheng. Og så må det uttrykkes tydelig og konsistent, sånn at folk vet at man snakker om det samme, organisasjoner klar over at det de samme problemene man skal løse. Og selv om Anton Ulvik har kalt det som her heter et need for desired outcomes, så betrakter vi allikevel behov som et mål på suksess, et suksessmål som en kunde i dette tilfellet setter på i hvilken grad en jobb han trenger å få gjort, godt eller mindre godt utført. Veldig raskt på oppsettet i Outcome Driven Innovation, som dette rammeverket vi lener oss til, så ligger en kjernejobb, en core functional job, som eksempler vi kommer til å komme tilbake til, å lytte til musikk, som består av igjen ulike steg. Man ønsker å klargjøre, kanskje bestemme seg for hva slags humør eller sinnsstemning man ønsker å komme i å lytte til denne musikken, før man kartlegger hvor musikken befinner seg, og så videre. Så det en sekvens på ting. Og i tillegg, for hvert jobbsteg, så har man noen krav. Og det kan være subjektivt, ofte det det, til hva som må være innfridd, og i hvilken grad for at dette jobbsteget, og i siste omgang, jobben skal være vellykket utført. Og det har en viss struktur, da kommer vi tilbake til det å uttrykke seg presist og konsistent, og det følger denne strukturen. Det har en retning, en måleparameter, en metric. Det som faktisk det man ønsker å se på, et object of control, og eventuelt en kontekst. Og eksempler her da, det å minimere sannsynligheten for at man må rydde hvis man har laget seg noen egg. Et annet eksempel som appliserer på det samme problemet, minimere tiden det da tar. Litt sånn kjøtt innledningsvis, så kommer brikkene til å falle på plass her etter hvert. Rammeverket vårt, det skal besvare en rekke ting, kanskje viktigst. Hvilke av organisasjonens nåværende produkter og løsninger som kan bli gjort billigere, i hvilken grad det kan bli forbedret. Hvilke segmenter som har de ulike behovene, og hvilke forbedringer man kan gjøre overfor ulike segmenter. Hvordan man kan markedsføre det mer effektivt. Og hvordan behov som i dag ikke dekket, best mulig og mest effektivt mulig kan dekkes. Overordnet så ser rammeverket sånn ut. Det har 6 steg. Man begynner med å definere den overordnede jobben som vi dekket i sted. Så graver man dypere, rent kvalitativt, for å komme frem til suksessmålene og de ulike stegene kunden må gjennom, eller brukeren må gjennom. Når man har en kvalitativ forståelse av hva disse så lager man en survey og kvantifiserer de. Og den eneste måten man kan få kvantifisert det på, jo da å ha en tydelig struktur på problemstillingene, som dere så i sted. Minimere tiden det tar, og så videre. Med det kvantitative utgangspunktet, som man da ideelt sett har et representativt utvalg av det markedssegmentet eller det marked man henvender seg til å besvare, så får man innblikk i de relative segmentstørrelsene, forskjeller mellom disse segmentstørrelsene, hvilke jobber, eller desired outcomes, eller needs som dere vil, som dekket i tilstrekkelig grad, i utilstrekkelig grad, og overfor hvem. Og fordi de formulert på den måten de så har man også et godt utgangspunkt for å foreta produktutbedringer, uten å bruke mange iterasjoner, kommer litt tilbake til det også. Den segmentinnsikten kan gi utgangspunktet for ulike strategier, enten for markedet totalt eller for ulike segmenter. Og så har du et veldig godt utgangspunkt til å konseptualisere konkrete produktutbedringer, nye produkter, henvendelser til nye markeder, og så videre. Noen av fordelene som kommer ut av dette har jeg dekket i og for seg tidligere, men jeg har lyst til å peke litt på at man også kan få et innblikk i hvilke behov som man i for stor grad dekker til de aktuelle segmentene. Hvis man bruker mye ressurser og mye tid på produktutvikling, på features som er lite verdsatt, så er de ressursene bedre benyttet andre steder. Man kan også benytte, som dere ser, beklager. Så kan man kartlegge relaterte jobber, tilstøtende jobber til hovedjobben, som gjør at man kan vokse markedet sitt. Man kan se utover de segmentene man forholder seg til allerede. Og i forbindelse med kundereiser, for eksempel, som vi jobber en del med i Knowit, så har man plutselig tydeligere svar på hvorfor kunder og interessenter rangerer de ulike stegene i kundereisen som de gjør. For det har vi faktisk nå statistisk påvist gjennom denne kartleggingen at skyldes disse og disse tingene. Og dette er imøtegått for liten grad og så videre. Og så har man et helt annet utgangspunkt når man skal begynne å utarbeide og iterere på forbedringer, også i kundereisen. Rammene rundt selve forbruket. Yes, og dette kan jo naturligvis da synliggjøres for hele organisasjonen, og det gjør det mye enklere for ulike produktteam og ulike avdelinger å jobbe mot det samme målet. Raskt et eksempel da, som jeg nevnte i sted fra musikkbransjen. Her har vi et utvalg needs, husk at det ble kalt desired outcomes i det rammeverket vi lener oss til. Langs y-aksen på venstre side, og så ser vi ulike teknologiske løsninger fra venstre mot høyre. Vi går fra LP til CD, til MP3-spiller, til streaming. Og basert på minus og plussene så kan man jo da diskutere hvorvidt det stemmer i hvert enkelt tilfelle. Men poenget her er at disse behovene, de står seg uavhengig av teknologi. De kan være der i 5 år, i 10 år, i 15 år fremover. Så når et selskap har mappet opp de behovene, så vet de hva som faktisk kreves for de segmentene de nå henvender seg til. Og så kan de gjerne gjøre nye målinger og finne ut i hvilken grad har våre anstrengelser resultert i høyere tilfredshet eller lavere tilfredshet. Men det denne oversikten her er ment å vise, er det at på tvers av teknologiske løsninger så blir de jobbene her gjort i dårligere eller bedre grad da. Yes. Sorry. Måten man gjør det på er egentlig da, og det kommer Mikkel til å komme nærmere inn på, men det er å rangere disse behovene i henhold til viktighet for den subjektive respondenten, og i hvilken grad de er tilfreds med dagens løsning. Kort om det da, for dette er jo noe vi da utvikler, og man kan gjøre dette på liten skala for kunder eller enorm skala for kunder, avhengig av størrelse på selskap og ulike produkter, produkttype og så videre. Men for å dobbeltklikke litt liksom, på dette rammeverket, få det litt mer, gå litt i dybden på det, så lagde vi denne kaffepiloten, for egentlig da å få hendene våre rundt noe data som var lett tilgjengelig, fordi alle stort sett på kontoret her i hvert fall har et forhold til kaffe, en preferanse og en tanke rundt det. Da. Så de jobbstegene vi da fant ut rundt den jobben å forberede en kopp kaffe, så var det å beslutte hvilken kaffe de skulle beslutte at de faktisk hadde et behov for å drikke kaffe, komme seg dit de kunne få tak i det, lokalisere utstyret som var nødvendig, forberede, gjøre tilpasninger gjerne under forberedelsen, også veldig avhengig av hvilken løsning man ser på her. Rengjøre utstyret, i mindre grad relevant for de som bruker maskin for eksempel, og så smake på å drikke kaffen. Og hver av disse stegene så kartla vi totalt 70 ulike behov. Alle respondentene hadde ikke alle disse behovene, men det var totaliteten av de behovene vi avdekket gjennom de intervjuene vi holdt. Og Og så tanken her at for de behovene vi ser at har relativt høy viktighet, men lav tilfredshet, så er de underlevert. Det er ikke imøtegått tilstrekkelig grad for det gitte segmentet. Tilsvarende kan man si om de som da har lav grad av viktighet og høy grad av tilfredshet. Og dette danner utgangspunktet for de ulike strategiene man kan implementere. Yes. Det tror jeg var min del.
Så litt om hvordan gjør vi det da? Og for å ta oss kort igjennom, la oss oppsummere hvorfor det egentlig er viktig å segmentere markedet. La oss deretter også se litt på hvorfor clustering egner seg til å gjøre det. Og så ser vi også på hvordan vi da faktisk anvendt dette i kaffecasen. Vi segmenterer naturligvis, som Vemund var inne på, fordi one size doesn't fit all. Skal du konkurrere og selge ett produkt som dekker hele markedet, så vil du brått ikke imøtekomme behovene til alle personer, fordi folk rett og slett har forskjellige behover. Litt av det man har lagt til grunn her er liksom at the average customer doesn't exist. Noe som man faktisk ser ganske tydelig ut fra de funnene som vi selv fant da vi tok og la opp alle disse 70 behovene på et ark, og egentlig så at de samler seg ganske sentrert på midten. Du kan se at det er noen som er relativt underserved i forhold til andre, men du kan i grunnen ikke si så mye. Så for å eksemplifisere akkurat hva det betyr, det er at hvis du har et behov, minimere tiden det tar før kaffen faktisk blir drikkbar temperatur, så kan en helt gjennomsnittlig score for populasjonen som helhet ikke si deg så mye. Men så kan man tenke seg at hvis du da kunne segmentert opp i populasjonen, kanskje vil du kunne klare å dele det inn i 2 ulike segmenter, og brått se at oi, her er det noen som er dødsmisfornøyde med at kaffen er for varm i det jeg begynner å drikke det. Hvis du finner et annet eksempel, eller en annen segment, som er helt overserved, som Vemund snakket om, som i grunnen ikke bryr seg, og som egentlig er ganske tilfreds med at kaffen kan stå litt. Og grunnen til at clusteranalyse egner seg, i motsetning til andre løsninger, er fordi det tillater oss å gjøre segmenteringen uten å gjøre noen antakelser om de personene vi har spurt. Altså rett og slett bare basert på behovene deres. Dette gjør jo også at vi også får statistisk grunnlag til å kunne si at dette er et cluster som skiller seg fra en annen. Og dette er egentlig, kontrasten ville jo for eksempel vært å segmentere på alder, hvor du bor eller kjønn, men da har du på en måte sagt at jeg tror at folk som er eldre eller yngre enn andre har ulike preferanser enn de andre. Mens dette er jo det vi overlater til algoritmen. Som selvfølgelig er egnet spesielt godt i dette tilfellet når det ikke er noen fasit. Altså i motsatt tilfelle, så hvis du har spurt en PC om å se på et bilde og se om det er en katt eller en hund, så ville du til syvende og sist hatt en fasit, fordi du ville visst om det var en katt eller hund det var et bilde av. Men her er vi bare egentlig interessert i å se i mønstrene mønstre i behovene til de ulike kundene, og se om vi på et eller annet vis klarer å clustre dem sammen i segmenter. Så det vi egentlig da prøver å gjøre er at vi da har en mengde kunder som har 70, eller beskrevet behovene sine på 70 ulike desired outcomes eller behov, og da sånn sett prøve å allokere eller segmentere dem, eller allokere dem til en gitt cluster. Og det vi har brukt er hierarkisk clustering, som i utgangspunktet har 3 overordnede steg. Du må på et eller annet vis klare å gjøre deg opp en mening om hva som er avstanden mellom behovene til, eller hvordan du kartlegger avstanden mellom behovene til kundene. Deretter finne ut hvordan skal man egentlig segmentere dem, kommer litt tilbake til det, og så gjennomføre clusteringen. Så når vi da knytter oss til avstand, så tror jeg egentlig det lar seg best vise med et eksempel. Så hvis vi tenker oss at vi har en kunde her med 3 ulike spørsmål, og en annen kunde, ON, som har de samme 3 spørsmålene, men har besvart litt annerledes, så vil det naturligvis være en gitt avstand mellom disse besvarelsene. Og hvis man summerer disse avstandene mellom disse strekene, det kan være Manhattan-distanse, det kan være kvadratisk distanse, det kan være alt mulig, så har man på et eller annet vis et avstandsmål. Men poenget her er jo å clustre dem. Man skal jo liksom si at disse her er nå samme person, så det er jo derfor man på en måte allokerer en cluster i midten, som sier at nå har vi på en måte skapt en ny person som definerer snittet av behovene til person 1 og person 2. Da forsvinner jo de og blir en cluster. Problemet her da er jo at da blir det jo på en måte en unexplained variance som på en måte ikke som blir større jo mer forskjellige besvarelser til person 1 og person 2 er. Og det er nettopp denne avstanden som kan gi oss en indikasjon på hvor forskjellige besvarelsene til de ulike personene er. Så ved å summere denne unexplained variancen i et cluster, så kan vi egentlig plotte dette opp. Det er sikkert kjent for mange, men jeg skal vise et eksempel. Så dette er et såkalt dendrogram, som sier at hvis du for eksempel skal ta clustere sammen person 1 og person 6, så er det en relativt lav i forhold til mange av disse avstandene mellom disse personene eller det blir en relativt lav avstand mellom person 1 og person 6. Mens hvis du skulle clustre sammen hele den gjengen til venstre der, så ville det vært en desto større avstand, altså nettopp at den avstanden mellom svarene til alle disse respondentene blir desto større. Og sånn sett kan man egentlig da sette seg en terskel på liksom hvor finner jeg et akseptabelt nivå da, av avstand mellom clusterne, som da sier at ok, egentlig blir besvarelsene i hver cluster mindre konkretiserte, men vi får på en måte dannet clustere. Eller så kan vi si at vi er litt strengere. Vi tar og senker terskelen for et strammere cluster, en mer presis cluster, men får da kun, poenget er at der har vi en rekke, eller der har vi samlet egentlig inn i 4 forskjellige clustere, mens her så ville vi egentlig hatt 2 primære clustere og en sett med ytterligere. Men til gjengjeld så er disse 2 clusterne vesentlig strammere, de er likere hverandre i hvert cluster, som gjør det på en måte lettere å kunne si at disse 2 clusterne skiller seg fra hverandre. Og, sånn sett, og det betyr i praktisk sammenheng, er jo egentlig at det vil forhåpentligvis være større forskjeller mellom behovene til det ene clusteret og det andre clusteret. Og ja, så går algoritmen sin gang og clustrer sammen fra bunnen oppover. Så hva betyr dette her egentlig i praksis da, i kaffeeksempelet vårt? Denne tok Vemund dere gjennom i stad. Og som dere husker, vi ønsket å prøve å finne ut hvilke av disse segmentene som er over-underserved. Her tok vi og plottet disse ulike stegene utover et kort. Utover nettopp den samme planet, hvor disse behovene egentlig gjelder for populasjonen som en helhet. Som dere ser, det er noen som spriker litt, men vi klarer egentlig ikke se noen særlig forskjell med populasjonen som en helhet. Men hvis vi tar og clustrer dem på den måten her, ikke sant, så ender vi faktisk opp med å få ganske slående forskjeller og et segment som viser seg å være vesentlig mer underserved enn det andre segmentet. Og husk nå at dette er jo basert på de 70 behovene som ligger under, og som beskriver hver av de prikkene, så hver prikk her er ett jobbsteg, og under dem ligger det 70 forskjellige, eller en av disse 70 behovene, som egentlig da klarer å si at vi har 2 ganske forskjellige behover, eller 2 forskjellige segmenter som er ganske forskjellige fra hverandre i hva slags behov de har. Hva betyr det i praksis? Jo, ved å drille litt lenger ned i disse enkeltbehovene, som for eksempel kan være jeg synes det tar lang tid før kaffen blir drikkbar, og det irriterer meg masse. Det kan være en av disse 70. Så har vi egentlig klart å skape noen ganske interessante profiler på disse 2 clusterne. Så hvor cluster 1 er, hans primære motivasjon er drikke kaffe for å være produktiv på jobb. Hygiene er ikke så nyttig for han. I motsetning til person 2, som drikker kaffe i mye større grad for å oppleve nytelse. Han drikker det for han liker varmen av å holde på en kaffekopp. Han syns hygiene er kjempeviktig. Han syns kaffemaskinen egentlig i stor grad er ganske ekkel, fordi han vet ikke helt hva som foregår inni der. Irriterer seg i stor grad over at du ikke kan justere styrke, mengde, smak av kaffen. Mens dette er ting som ikke interesserer en klassisk person i cluster nummer 1 i det hele tatt. Så der hvor kanskje cluster 1 er opptatt, eller det han riktignok er opptatt av, er å ikke skitne til pulten, sånn typisk den der kaffesirkelen som danner seg når du setter ned en litt sølt kaffekopp, som kanskje også kan gi mening, fordi cluster 1 er en sånn typisk fort og gærlig person, da, utifra hva vi har sett i dataene. Så liksom, hvis man da skulle kontekstualisert det over i hvilke råd man skulle gi denne kaffeprodusenten etter å ha gjort hele denne analysen, så må det jo være noe slik. Altså, hvis man tar disse kaffemaskinene som man har i dag, som egentlig i stor grad er Rolls-Royce, og hvor du kan liksom velge cappuccino og gudene vet hva, så kunne man egentlig bare tenke seg at cluster 1 helst skulle foretrakte en kaffemaskin som du kunne trykke på en rød knapp, relativt raskt få en kaffe, og da sørge for at han har noen lokk som gjør at han ikke søler. Han er overserved, som Vemund snakket om, ikke sant? Så ta gjerne en billigere pris, eller øk marginene dine, eller what not. Mens helt motsatt for det andre kløsteret, som er vesentlig mer opptatt av smak, intensitet, eller å kunne endre på volum og intensitet på kaffen. Hygiene er vesentlig viktig. Vi byttet faktisk kaffemaskin, vi presenterte faktisk ikke funnene i forkant, det er egentlig litt leit. Men en av de tingene som faktisk har skjedd, da er jo nettopp det at den nye kaffemaskinen sier ifra når det ikke er melk igjen på kontoret. Så liksom for cluster 2 så tror jeg de allerede er ganske vesentlig mer fornøyde da, ved at liksom, før var det sånn at du trykket på melk og så fikk du noen skvip-vann-greier. Så det er en stor forskjell her. Så det jeg synes er kult med dette er at vi på datadrevet vis nå har kommet frem til svar, eller anbefalinger, som vil vare over tid. Ikke sant? Behovene er helt uavhengig av hvilken løsning man har brukt. Du kunne like gjerne vært anvendt på de som foretrekker presskanne, eller traktekaffe, eller hva nå enn. Noe som gjør at de vil holde seg over tid, og vi vil kunne gi veldig håndfaste og angripelige anbefalinger til kunder. Takk for at dere hørte på. Spørsmål?
Ja, er det spørsmål? Da har vi selvfølgelig blikset litt på antallet. Vi har en liten gave.
Enestående.
Koser dere.
Takk for den.
Takk. Da tar vi en 5 minutter pause, hvis vi setter opp neste presentasjon. Så bare tar vi snacks og går på do.
Hallo. Da starter vi opp igjen. Nå skal Per Bur snakke om Argo.
Yeah.
Yeah.
So first, would anyone like me to do this talk in English? Yeah. Yes, please? Yeah. Yes, okay. I'll do it in English then. Okay, data pipelines with Argo, or cloud-native data pipelines. So sort of jump right into it, and I thought I'll sort of just explain what a dialect acyclic graph is. I assume most of you know it, but I'm just making sure that everyone's on the same platform. So basically, a dialect acyclic graph is a graph with no loops, so that basically you can only move sort of forward. The idea being you take some sort of data, you process it in steps, and sort of at every time it sort of moves ahead. It never goes back. Yeah. Yeah. So with that out of the way, this is me. I work in Knowit ObjectNet in the principal engineers team. Previously, I worked in Limpro, Varnish, and IncludeOS. Currently, I'm doing sort of architect or prototyping stuff at the National Archives. I don't really know much about machine learning. I've been sort of dabbling a bit in it, with it the last couple of months, and I'll talk more about that later. But I had this need at the sort of archives to actually process quite a bit of data. And I sort of started looking into some tools. So what they actually do is they take archive dumps, which are typically 50 to 800 gigabytes of data collected over a number of years, and they process it in various steps. They're actually starting to consider using some machine learning on to do some metadata extraction on it, but that's not really the focus. The focus is take a bit of data, process it. So when I started sort of looking into it, a tool that was sort of commonly talked about was Apache Airflow. So it's a very sort of mature implementation of a workflow tool. It came out of Airbnb 5 or 6 years ago. So the fact that it sort of was born in 2014 is actually I would say the reason why there's something wrong with it, because 2014 is a long time ago. The thing I really liked about it is that you write your Airflows in Python. So for those of you who sort of had to sort of struggle with sort of these GUI workflow tools, writing thing in Python is quite convenient because you have access to everything. It's so much easier to debug than anything other. So when Airflow started out, I think like it was the way that it would sort of execute a step was to use Celery. So Celery is this implementation sort of a producer-consumer pattern where sort of you give a task and you put it onto a queue, and there's some consumer that is listening to that queue, picks up the tasks, execute it, and then puts the result back somewhere. And then there are, what I found interesting was with it when I sort of was evaluating it, was the support for Kubernetes, which was sort of, I would say, a more generic way to sort of execute steps in a workflow. So what's wrong with Airflow? The underlying thing that sort of I really disliked about it is that every step in an Airflow workflow needs to have Airflow inside it. So this is when I was running on Kubernetes. So every container needs to have Airflow installed inside of it in order to actually do the step. So I mean, for sort of traditional ML step, like a training step or something, that probably not necessarily that much of a showstopper. But if you want to sort of have this super generic, like a high-level overview workflow where you want to sort of have maybe 3 or 4 different teams working on different steps. Having all of them having to know this very particular tool is not really that nice. So at that point, I sort of stumbled across Argo. Basically meant that it is cloud native. So cloud native, is that like a... Do I need to say what cloud native is? Yeah, I should say what cloud. So a cloud native to be run in a VM doesn't rely on sort of local storage. Typically, sort of it is encapsulated container, and that container can sort of appear magically, work for 5 minutes, and then go away. That means that there are a lot of rules that you have to abide to, or 12 rules exactly, on how that application should behave. So Argo, the steps in an Argo workflow, for that to work, it needs to implement all of them. Or, yeah. So Argo uses, it's pretty similar to Airflow, but it uses Kubernetes for scheduling and execution. And the win was that the container doesn't know anything about Python or Airflow, so it can be anything. Also, what I sort of found really nice was that as the sort of workflow progresses, you produce some artifacts. I think that, for me, that was one of the sort of biggest gains I had from using this compared to something I would write myself, was that it sort of, you could spit out artifacts and it would handle it for me and move the artifacts from step to step. I'll talk more about this now. So during a workflow, the artifacts are sort of the files that are created while you do some sort of computation. What Argo does for you in each step is that before that step starts, it will inject the artifact into the container that you're running, or into the pod that you're running in. And then the step runs. And then after the step has completed, Argo will again go in and pick up any artifacts that you have created or modified and sort of put them back in the store. So for me, basically did 2 things. One was scheduling, like run this after this has finished. And then when step 2 is being executed, it has picked up the artifact from step 1 and injected it into that container. Is that clear? Yeah, great. Yes, and Argo has AWS S3 client built in. I found that to be service, which is a S3 compatible object store that could run inside the same cluster. And that's both more performant because I don't have to talk to S3 in Finland or wherever. And it also sort of means that the cluster as a whole has fewer external dependencies. Now there's this thing that Argo has, because it's a native Kubernetes application, it relies on YAML. And this is my pretty simplistic workflow. So I'll try. Do you have a laser pointer? No, I don't. Okay. So we'll see. Maybe there's one in. Is there a way to get a red dot? Huh? I don't think it works. Yeah, but isn't there something in Keynote where I can push some button and it sort of there's a red dot or something? It used to be, at least. Okay. A laser pointer. Excellent. Thank you. Yes. So okay. So we'll try to sort of. So what's this? So that's basically what sort of resource this is. So this is the demo. This is where it starts, and this is the DAG itself. So the direct acyclic graph. It starts here. So this is the first task, which is generate. So the first, and it uses the template generate data. That's defined further below. So you can sort of keep the DAG definition and the actual tasks, which are a bit more complex, further down. So generate will pass data on to consume, which has a dependency on generate. This is basically how the actual graph is implemented, is through these dependencies. So consume uses, and here we see sort of, I'm trying now to sort of inject an artifact into it. So I take from tasks, so that's from this workflow, and from the template Argo cat. So this is the generate data step task, set.txt. Numbers from /tmp dataset.txt. So that's basically how it works. This is just because it supports compression of artifacts, and this is just a way to disable the compression. I think I'll just, this doesn't do anything exciting. It just basically opens the artifact and sums it up. So it sums all the numbers up. Not really that much exciting. It has both inputs and outputs. That's what's, but as you can see, they're more or less identical. And this is the last one. And here's sort of one thing I would just sort of dislike a bit about sort of Argo. There's many ways to sort of skin a cat, or many ways to sort of define a sort of template. And as you can see, I don't use the script, I use container here instead. So that's slightly different and has slightly different semantics. And I'm not entirely sure that they should have added that. I think it might have been easier if they sort of had one way to do things. So this one just references latest version of Alpine, and it does just runs cat on that particular file. Yeah, and it has an input defined. Was that was okay, wasn't it? Yeah. Demo. Yeah, so this is, okay. I have this. I usually don't use this terminal because, oh, I don't have a network. Oh, yeah, I do. It's just very, very slow. Okay, so there's a one node cluster running in Google. That's my Kubernetes cluster. So, oh, I can just show you this file. So this is the file that I've just gone through. Use the CLI even in automation. Utilizing. No, okay. So, things I've learned so far. There's a bug in Argo which really annoys me, that all tasks are evaluated, even if they're not supposed to be executed, because you have things like conditions. So you want to say like, this step should only run under certain conditions. Like it's for instance, you want to reject data, and then you don't want to run all the steps. It will still evaluate all the steps. And if it can't find the artifacts for all the steps, it will mark the flow as a failed flow. It's been the bug report has been accepted, and they will likely fix it at some point. I find the syntax perhaps too flexible, and when these workflows get into like 1,000 lines or 2,000 lines, they get long and complex. It's YAML, and it's debugging it is sometimes painful. You have to sort of stop and check a lot of the time when building the flow. if you sort of write 1,000 lines of YAML and then just expect it to work at the first try, you'll be sorry. Yeah, and the decisions, like if you do this with Airflow, you have all the tools in the Python tool chest in order to sort of only execute this step on a Wednesday if it's after 1 o'clock, right? You can do that's easy in Python. It's not easy in YAML. You can do it, but you have to sort of create an extra step that will sort of then where you stick the Python in that step, and then you have to sort of output an output variable and then do a condition on that. Documentation is mostly in the form of examples, which is sometimes really nicely, but since there are so many ways of solving the same thing, you have 5 different examples that are sort of similar but not the same. So for instance, you don't have to define the workflow as a DAG. You can use it in the first format, which was steps, which is completely different. And these examples mix and match, as some of them are using DAGs, some of them are using steps. It's not always, you can't really just cut and paste from them and sort of mix them together and expect it to work. Yeah. That's it. There's tons of stuff I haven't touched on. There's loops, for instance, which are interesting. I think you actually can have things which are not really DAGs, like you can retry a step again and again until it succeeds. It's not really strictly a DAG. Community is pretty helpful. There's a Slack channel. That's not that helpful for beginners, but if you file issues, they're really attentive. And they guided me through the first bug I submitted. Instead of solving it, they told me how to solve it. And they spent quite a bit of time to sort of bring me on as a contributor, which I found nice. Questions? Okay. Then I think I'll introduce the next speaker, which is Jon Nordby. And I'll I'll tell you a little story about sort of why I brought Jon Nordby here. Because earlier this year I had this idea of a startup. I thought I probably won't turn into anything, so I thought I might as well sort of share it with everyone. Last summer there was this documentary on the TV about sort of farmers abusing pigs, and that sort of stuck with me. And I thought, like, why don't we put cameras in the no, not the barn, the
So, thank you so much, Per, for both inviting and introducing. That's very nice. I'm here to talk about classifying sound using machine learning. We will not use animal welfare as an example, but that is a relevant example. And I know people that are working on maybe not the abuse part, but making sure that farms operate well and that you find out when things are not going well. So, about me. I'm a specialist in Internet of Things. I have a bachelor's of engineering in electronics from about 10 years ago. But I spent most of my time as a software developer since then, both working on embedded systems, so that's still staying in the electronics land, and also on web. And then I took a master's degree in data science 1 year ago, completed. Now I'm the CTO of Sound Sensing, where I try to combine all these skills into products. So I wrote my thesis on environmental sound classifications on microcontrollers using color vision. Very long thing, but basically trying to be able to classify environmental sound in this case, so noise, typically noise from cities, on a edge node. So you can do it directly on a sensor. I forgot to bring my sensor. It's somewhere around. I will have to just show it. There it is, our sensor unit, which can be battery powered and detect noise. An important thing here is that we don't need to send the sound itself, so the potentially recordings of people or with all the GDPR constraints on, we just do the classification on the sensor node and send the information that we're interested in. Someone stop praying for a second. Send the information that we are interested on, which could be a noise source. So like, okay, here, hopefully the main noise source is the tram or the T-bane, and that we are interested in. So that's what we provide at Sound Sensing. We do solutions based on this technology, including, for example, noise monitoring. So you can not only know that, yeah, the noise level here is too high, according to regulations, local or EU-wide, but also understand what is the sound that is causing this problem so that we can do something with it. So this information needs to be actionable. And the goal of this talk is that you as developers, so I'm assuming that you know something about software development, have a little bit of familiarity with machine learning, that you will understand the possibilities and applications of machine learning on audio. So what can we do with this? And the overall workflow of creating a solution that with audio classification. Audio classification is one subtopic of machine learning on audio. And then learn a little bit about what sound sensing, what we provide in this area. So background. Why audio classification? Why are we interested in this? How is it useful? So audio is a rich source of information in general. Like essentially any physical motion creates sound. You can't always hear it, but in many cases you can. And as humans, we use our sound in many ways. We use it for understanding the context, what's around us. Danger, for example, if you're walking near a road and you can't necessarily see the cars behind you, but you can hear them. That's very important. If you work with, say, manufacturing or machinery, good machinists they have usually a very good ear. They can hear, something is not right here. This needs to be looked into. Or sometimes they can even tell you exactly where inside this machine there is a particular problem right now, which needs a lot of training. And the interesting thing with machine learning, and especially with the last couple of years, 5 years or so, we can do near human level performance. So we can, if we have the right data and the right way of modeling the problem, we can implement that expert machinist. And that's very interesting. And also, so there's many applications of this. Of course, audio in general, there's a lot about speech recognition. Of course, we care about sound and communicating with sound with each other. Music analysis. Music is very interesting, and lots of audio machine learning goes in there. But it's also like, let's say, the general sounds. So sounds of a city, sounds of machinery, sounds of maybe people's activities. You don't care to recognize their sounds, but they're making noise, for example. So in ecoacoustics, you use sound to analyze bird migration, to understand, for example, how climate change affects birds, and you need to understand, you need to somehow log the birds, and you can do this with sound. You can do wildlife preservation, where, for example, in an area where you're not allowed to cut down trees, if there are a sound of chainsaws, that's a cause for investigation, right? In quality control in manufacturing, so for example, I know that car seats these days are modern. They have a lot of motors and stuff, and they all need to work. There's like 7 motors in the high-end car seats, and they test them using sound, because you need to test the final product, and you can't really put your testings into or change the car seat. It's already done. You just want to check that it works. So they test it from the outside using sound. That's very powerful. You can do non-invasive monitoring, as it's called. And in medical, doctors, and also this is happening with even some apps these days, you can detect possible heart problems by listening to the heart. And in process industry, there's you can, for example, automate the process. And then there's a coffee machine company here in which I've been working a little bit with prior to sound sensing that uses sound to detect when the coffee is properly roasted. They're called röst. Yeah, and one thing that's also interesting, there's a lot of applications, but we have also a technology landscape. So machine learning is going fast forward, and that's improving rapidly. But we also have, and that's on the, let's say, software modeling and training side, we can do more and more with that. But also the question is, how can we put this into a real life situation? We need this to be done, like not all applications can afford, for example, a full PC with a NVIDIA card and so on running in that scenario. You need a lightweight solution. And then basically all the manufacturing of microcontrollers, they have announced that they will implement in hardware accelerators for neural networks. And that is expected a 10x increase in power efficiency for sensor units like the ones that we provide, which is something, it's another wave that's coming fast. Makes this very interesting. So how do you make an audio machine learning solution? What are the steps? What are the pitfalls? How to approach this? So the overall process, you need to start with problem definition. Of course, you need to think about what problem you want to solve for your user or for your customer. What are the considerations about that? But also you should define it down to, let's say, a task, so that you can, instead of like, oh, we have this animal welfare detection thing, or like what task is that called in the literature, so that you can find, let's say, established solutions for it. You will need to collect data, because unlikely your particular problem has a data set already. You need to label the data, which is quite interesting, often ignored. We'll talk about that. Training setup, gets more into standard machine learning. It looks very similar to any other, if it's image or text or so on. Feature representation, so we need to worry about how do we model this audio, and we need a model that can do the classification that we're interested in, and then we'll evaluate our solution and deploy into production somehow. So our task, to keep things concrete, we'll talk about noise classification in urban environments. This is what we work on mostly right now, so it's good and concrete, and it's widely researched. So, well, depending on how you search, if you use the term environmental sound classification, you'll get around 1,000 hits on Google Scholar. If you search for noise classification, you'll get near zero. Another important thing, well, just knowing the name gives you superpowers with Google. So I'll give you some names and some terminology along the way. So in 2017, it's estimated on one data set that machine learning models have approximately human level performance on this kind of task. So it's like detecting, okay, is it car noise? Is it children that are playing on the playground that's making the noise? Or is it music on the street? So that's the task. And what we will apply is supervised learning and machine learning. I'm just in basic introduction to this. The amazing thing here is that we have a set of sounds in small audio files, for example, and they each have an annotated, so the ground truth or target of what is in this sound with car traffic, speech, so on. And then, okay, you can't really see it, but at the end what we want to model, and at the model we can feed in a new sound and get a prediction out of what was it. Was it speech or car or so on? And in this black box is all the magic, the machine learning, that will pop out this model. We will open that box a little bit and see what, because in theory this is how it should work. Like you should just be able to do this, provide data, say what the goal is, and it'll spit out the model. In practice, you need to know a little bit more. So the training process for supervised learning can be seen as something like this. You have your training data, the sounds and the labels, so data and labels. And you need to also have these hyperparameters, which are things that you can't tune. Like, for example, how long of a window of sound do we look at at one prediction. That's it's possibly an important question, but the training process can't itself answer it. So we won't talk so much about that part. Hyperparameter optimization, it's well covered on the internet in general. We use the data and pre-process it. That we'll talk a little bit about. And then classify, that's our model, like the core of the model. And this makes some prediction, computes some error based on the labels, and the model is adjusted. And this goes around and around, and eventually that classify bit is good enough to be used on your new data. So yeah, classification. So classification, audio classification, that's one task inside machine learning on audio. A classification is that given a sound clip, so it now has a fixed length, it's not infinitely long like a stream of audio could be, with some sounds in it, determine which class these sounds belong to. And there's some important simplifications in classification. We have a single output, so we say like no matter how much sound, there could be any number of sounds going on at the same time, we will have a single output. So we have only one class at a time. It's discrete, so the sound either exists, or the speech, for example, either exists in this thing or not. It doesn't estimate how much speech or so on. And it's closed set, and this is an important limitation that people often forget. It must be a known class. So, okay, we have trained it on, let's say, traffic and construction noise, and let's say human noise, so speech and music and so on. These are the three classes. Now, if you put in something else, for example, bird, like some animal noises, it doesn't fit in those three. What will the system do? Unless you make some corrections for it, it will output. It will choose one of those three. Like that. That's the how you've set it up. So it will make a bad decision because you're feeding it data outside its known set of classes. There are some ways of compensating for that, but this in general, you can only predict something that you have predefined. And these simplifications all give limitations to the system. However, they also make it an easier task to deal with, which is why we do them. And audio classification is therefore kind of a base task in audio ML, and other tasks like audio event detection, where you want to be able to know, okay, when exactly did particular sound occur? Like, give me the start and the end of speech, for example. That's usually built on top of classification. And anomaly detection can also be seen as a kind of a where you want to tell them, like, okay, tell me whether this is a new sound. I don't care which sound it is, but it's a new sound or different sound. You can build on top of classification. So we'll focus in this talk on classification. Okay, so that's our task, and this will already help you on Google. Find my talk on YouTube, at least. But the other important thing is data, right? So we have some idea about our task and the way to approach it, but the other thing is data, and this is a key component. Like, machine learning methods are easily available. You can just download any open source framework, and there's tons of examples and so on. The important ingredients, which often you don't get for free, is the data that you need. So the key challenge in data collection is ensuring that your data is representative, so that the data that you capture for training is somehow close or on some level identical, very close to what you will be feeding it later. This can be a huge challenge if you have a product that will run on multiple phones, for example. They will all create different, for the same input sound, they will record a different sound. And also if you have a product that is in multiple countries, for example, the noise of sirens in cities, every city has sirens that make noise, but they're very different in different cities because there's probably even regulations about how a police and ambulance car should sound in Germany versus Norway versus America and so on. And this, if you don't have that covered, your model will be wrong, and we can almost guarantee you it will not generalize for that. And you need to have enough coverage So you need to, there's a variation inside your classes and variation between your classes, and you need to cover both of this. Otherwise you will hit this, oh, this is not similar to anything the model has learned. It will make a mistake. Like it will not, it's not, in this way, it's not like a human at all. It will make silly errors all the time. So, and you need to, data collection process is very important to capture the relevant metadata. So you will go out, capture some sounds. Important, like, there are many things that can affect how those sounds work. For example, distance to the source of the sound. The environment around, maybe so you're interested in T-bane sounds. If you only record those at the start and the stop of the T-bane, you will get a T-bane sound, different from the one that when it just passes in the forest or something. And you should capture all these things so that when you see that, oh, my model does wrong on this, you can use your metadata to understand why is it making this kind of mistakes all the time. Your models also have a tendency to, in general machine learning, to capture or to base their decision on irrelevant things. So if you would have particular noise on your sensor, for example, and it correlates with a certain class. So like if you used one recording equipment for one sound, the T-bane sounds, and a different recording equipment for speech sound, most likely your classifier will learn to classify what sensor you used, not which sound it was. So many things to be careful about. And that's why you should record in your metadata which device did you use, what type it was, and so on, because then you can uncover these patterns later and correct them. And of course in data collection in general, especially with audio, important to maintain privacy. So that's actually like half of our data collection processes is about managing that aspect. So good best practice when you do data collection is think about this thing up front. It's going to take quite a lot of time to collect the relevant data. So think about it up front and write a data management plan for how you're going to deal with this data. And that's where you take into consideration how you avoid your privacy problems, for example. And also make sure that you think about metadata and organization, how you'll store it, so that you will have maximum value of your data later. So you didn't spend hundreds of hours of collecting data and then missing some important metadata and have to, you have reduced output from your thing. So then you should write down a data collection protocol, because you should also be consistent in this process, and you should know, you should have a, let's say, well-defined way of capturing the data, so that you can, and which you will continuously improve as you do. So data requirements. So this is one of the reasons why so many underestimated problems in data and machine learning. One is the quantity. I mean, simply the quantity that you need. So in general, you would want to have 1,000 at least. I mean, this is considered a very small data set these days. 1,000 labeled instances per class. So that in urban sound is 10 classes. It's roughly that size. That's 11 hours of annotated audio. So not just 11 hours of sound, but 11 hours of relevant sound with only the classes of interest that have been labeled. So probably this means that it's collected 10 times, 100 times that amount of sound in order to get to that curated data set with annotated sounds. And but I've seen other cases, or like, for example, with this coffee machine project which I worked on, there we only used less than an hour of sound in total, because we had a controlled environment. It was inside a machine that we controlled, sensor environment that we controlled. It was only detecting cracks, like popcorn cracking sound, versus not. So it's only 2 classes. And because the controlled environment, the variation within the class, so like each pop sounded relatively similar to another pop. Unlike, for example, if you think about speech, different languages sound different, different people sound different. There are huge amounts of variation. The content, like you talk differently all the time, or you talk about different things. Huge amount of variation inside that class. And then the other question is, how much distance do you have in your classes? So if you have a lot of variation, that's one thing. But if you have two classes with a lot of variation, but they're very close to each other, it's going to be hard to make a distinction. It's going to be hard to make a good choice, like it's this or that. Sometimes you have classes which are overlapping. Like there are like if you have street music and speech, there are things that are street music that also is basically speech. So it's not possible to make a perfect distinction. And yes, that's an important thing here. So data labeling. So this is the act of taking your data, audio in this case, and putting a label on it. In this, if we do a classification, we just put, for a certain section of sound, we put this is speech, or this is construction noise, or something like that. The challenge is to keep the quality high and the cost low, because this is usually, or often, this costs a lot of money, because unless you find another really smart way, basically some human needs to go through all this data and label it. That's the human are our reference, and that costs money. So you might need expertise. If you're going to replace that expert machinist, you can't just use people from the street. They won't be able to tell you the right thing. So in that case, you might be paying someone 1,000 kroners per hour to go through your data, right? I might be paying them more. I might be paying them 2,500 per hour. So that it can be very costly, or it will cost. But key questions are like, what is the human level performance? Because you should not expect to exceed human level performance. You might hope to reach that, because it might not be possible to go beyond, or it might in some cases. Humans are not perfect either. But also, if humans are your ground truth, you will have you have a chicken and egg problem. You can't do better than the person that tells you what's right and wrong. So what is the human level performance? That's something you should evaluate in your labeling process, so you have an idea about what kind of performance can be achieved there at all. If humans can't do it, don't bet your business on that you can do it. That's not a good choice at this point. Also, annotated self-agreement. So if the same person labels the same sound twice, or 3 times, 4 times, 10 times, do they agree? I mean, like, do they agree with themselves? Is there consistency here? This is 2 levels. Like, so if every annotator that you have doesn't agree with themselves, then you have a vague problem, and that's just part of the nature of the problem then. Or how you've defined your classes. Maybe your classes should be more specific, or maybe they are context dependent, so you need to fix it a bit. And that's something you should, if you discover that, you need to correct for it. And the other question is then, like, how do you have inter-annotator agreements? So do 2 or 3 people, different people, agree with each other on what is this label? If you don't have that, it could mean that, again, it might be context dependent, culturally dependent, personal preference dependent, and so on, which you either might be in the nature of the problem. Maybe your users will have the same, let's say, fuzziness variation, or you haven't properly specified or corrected for this. So these are the key, like, let's say, ways of estimating how good is our labeling process and our data set. So how to label? You can outsource. There are data labeling services, at least for images. I haven't found any data labeling services for audio, unfortunately. So those are professional. They specialize in labeling, and they manage their own teams and so on, and they ensure that quality is quite high. The other approach is outsourcing, is to take Amazon Mechanical Turk. Just throw this as a task where people can do this for as cheap as possible. Of course, your quality is likely to be different, so you'll have to spend more efforts on quality assurance. Crowdsource, you can try to get the public. If you can make what happens when you solving CAPTCHAs, for example, these days, image CAPTCHAs. You're giving label data to Google as a side result, right? So, can you get the public to do it? Can you get your users to do it? In ecoacoustics, I know there's a website where you can label sound, and bird enthusiasts actually go and label sound. And that data set is publicly available. So, in-house, and this question, do you have a data labeling team? Do you put it in, data science team and so on? Or can you find some way of automating this? Because it could be very beneficial. So if you can find, for example, another data source, another signal in a sensor system, for example, that tells you whether something is the label that you're interested in, then you don't, well, then you might be able to do that for a lot of your things. So there are many annotation tools. We built our own, but based on an open source one called Audio Annotator, a very general name. And it's quite nice. So here you can, I haven't put in a section, but you can mark a section of sound. For example, here in the start, it looks like there's something happening. And there at the end, there's also something happening. Possibly very different sounds because of the way spectrograms look. You listen to that and you mark the region and you put a label on it, and also we let you annotate. Is it a close sound or a far sound or a sound that you're not sure about? And you do that for hundreds, for thousands of cases. And when you've done that, you get a curated data set. So you might have done other steps here too. For example, you might have removed some, if you find that there's some irrelevant data here. For example, when we go out and record, there's a lot of recordings in the start and the end where you hear the sound of someone taking the sensor down. So a lot of handling sounds. Those you don't want in your data set unless that's a relevant thing to detect. So that kind of things. If you have, at night, if it's near like recording in a T-bane, there's no T-bane at night in Oslo, so probably you want to skip those, or at least skip most of it. You might want to keep a little bit to represent silence or the environment around, but clean that up, and you'll you'll decide the classes and end up with something. And then you're let's say done with the first part of the audio. That's where you can think about the model. So often people, if you see things online, including the talk that I did previously, they skip data. Data magically appears. You download it on the internet, and then you use it. I wanted to cover this in this talk, a little bit at least. So how to deal with the audio. So now we're talking about the modeling. I will check the time. Yeah, we have a little time. So we have audio as our input. So this is a audio plotted over time. At the top there is a waveform. It's a typical time representation where the sound level increases up and down. And that is, if you have a sensor system, that's theoretically a infinite stream that will go on, until the sun stops. That's not manageable. So we need to cut this up into so-called analysis windows of a fixed size. Basically, almost all machine learning models need fixed sized inputs. And then we transform this audio into a spectrogram view. So in spectrogram view, you have frequency on the y-axis and time on the x-axis. So we basically have done Fourier transform on like very small sections, and you get this. And that allows you to separate many kinds of sounds. So low frequency sounds will appear near the bottom. Tones will have a relatively horizontal pattern, and knocks or like percussive sounds, or if you've seen them before, you can often, as a human, you can often see the different sounds. You can see, that's probably speech, or it's probably something else. Like this here is I don't think it's speech, I think it's music, because it has this chord-like pattern, each of those things, but I don't know. But so we do that transformation, and this is great in two ways. It allows us as humans to easily more see the data. It separates many kinds of sounds already and get meaningful patterns. And thirdly, it allows us to use basically image recognition to solve our audio problem. And that's excellent because image recognition is within the last 5 years becomes super good. So you can apply all the latest, let's say, technology and models and principles from image recognition, which is a much bigger field than audio, to your audio problem, to solve your audio problem. So that's a very big advantage of this approach. You can learn directly from the audio. It's being widely researched, some promising results, but I wouldn't call it, let's say, production grade yet in general. So our classifier here is the actual model that we're learning. And then because there's a risk that the label that we had was for a much longer period than 0.72 seconds or some short period, might be even for 5 seconds or so on. So then we need to somehow merge our individual, or we need to map between the label we have for a 5 second period to these individual windows. And the easiest thing is to assume that it was all the same sound inside that and kind of copy it onto each of those. But you need to then merge the results of your prediction, because your prediction will be per these small parts. You need to merge that into one prediction for your 5 second part. And the easiest thing here to do is either majority voting. So if 3 out of 5 was this class, okay, that one wins. Or you can do a mean on the probabilities for each classes. This is also called soft voting, which tends to do a little bit better. Both are fine. Yeah, and then after the voting, like so these would be, only show children playing, but for example, this could be street music, this could be another kind of class, and the highest one wins. So we can use the image model for this, and the standard best performing for that is convolutional neural networks, CNNs. So who here has heard of a CNN or worked with a CNN? Okay, so that's a fair bit. So yeah, they do excellent, and this here is shown a very simple one with 2 layers. Modern CNNs for image classification tasks have 30 layers, 50 layers, 100 layers, and are huge because they often deal with very complex problems like deciding of 1,000 different categories in ImageNet, for example, of images. Whereas most audio problems, if we exclude speech, deal with much smaller amount of categories. There's an audio set which has defined 631 categories of sound, but most applications that I see, or that at least people have approached us for interested in, are interested in sometimes 1 or 2 sounds, or 10 sounds, or something like that. So, and that means that the models that you use are often quite simple. So you can do, if you have an audio classification problem, start with a really simple CNN. Like start with 2-3 layers and something like that. This model here does, on this urban sound data set, is still near the top of performance. It has 3 convolutional layers and 2 dense layers. So it's a very simple model. And once you have your model and you put it into the training setup that I said before, and that's the same as if it was image classification or it's some sort of text or something. The training loop is the same. So you use your favorite framework, Keras, TensorFlow, PyTorch, whatever. Plug in data in the model, and out comes some results. So here's just shown some results from my thesis with different model variations. So in the thesis, I show that you can reach quite close to the performance of, let's say, the best models that run on PC, while still running on a sensor chip. And this gap is going to get closer, like smaller and smaller, especially as we get these coprocessors into the sensors. Okay, summarize. So to summarize on the audio level, wait, there is a, yeah, okay. For classifications, as long as you find a way to formulate your problems or what you care about in this audio task as an audio classification problem or audio event detection, there are standard models out there. This pipeline that I showed by splitting into fixed size sound windows, converting to a spectrogram, and then using a CNN will, for many tasks, get you all the way there or nearly. and it's all available as open source solutions, Keras, TensorFlow, and all these things. And my talk on at EuroPython, which is on YouTube, has a bit more details about, let's say, the modeling part. Didn't cover it here since so much other things to cover. Data collection is not magic. Sadly, data collection is something that, for example, online and even in literature and books is not really covered. It's like, well, yeah, you just do something, and then you get a data set, and then you have this data set, and that's great. Or they don't even say that. You just like, oh yeah, you just find a data set. Okay. For some problems, there are large open data sources, but of course, it might not apply directly to your problem, and you have challenges if you try and reuse an open one, where, for example, what if what you are interested in is not well covered? Then you'll have this kind of coverage problems. Or it might just be that for the task, there's no relevant data online. Like no one has that kind of data, or at least willingness to publish it. And also, if you do only on open data, you can't really be much better than your competitors because they all have access to the same models. So data is a competitive advantage as well. So, which might be why no one documents how to do this in any detail. But at least I've told you a little bit about what things to think about, and it's mostly about structuring your collection up front so that you make sure that you take this task seriously, and you budget the required resources both for collecting the data and for labeling the data, and that you integrate quality checking. So you don't assume that, oh yeah, we have labeled data, it must be perfect. It's not. It's an artifact of the process that you set up and let's say the natural world, the natural variation that you have. And both of those are open questions. Like you don't assume that you know that enough about those. Like put some checks. Do people agree with each other on this task? What is the threshold? Like, is the expectations of the customer higher than what is humans can do? Then you probably need to talk to your customer and say, this is not the best expectation. And build it up gradually. Start small, do iteration, evaluate, quality, improve, and then, so it's doable, but it will take time. And all the clients and people I worked with, this is the big surprise. I don't know why that it takes much longer than you think. It takes 10 times as more effort than you think usually. And So we went through this process. We have a model that can, that run on our machine and give us some results on our testing set. Says, oh, it does 90% correct, which maybe is not near human level performance. Okay, but we wanted to monitor a real world phenomenon. We wanted something that will work in the barn, or something that will work in the streets and so on. How do we deploy this? And that's, so there's a couple of things here. You need to decide on a strategy for dealing with the data. So one approach would be to send all the sound from your sensor to the cloud, to the server, and then do the classification there. Then you can use exactly the same model that you have trained on your PC and tested already. However, you will now, or depending on the environment that the sound is captured, this might be okay privacy-wise, or it might be completely not okay privacy-wise. Even it could be legal challenges with that. So that's that. But if you have a room where there are no humans, this might be an acceptable approach. It still is. It's also data transmission-wise the most, the one that requires the most energy. So that will limit your ability to put your sensor on a battery and so on. But it might be okay in some circumstances. You can do the spectrogram conversion on the sensor and send the spectrograms over. This will at least compress your data quite a bit. Depending on how you structure your spectrogram, if it's very high resolution, you can actually invert this into sound again, so you have still privacy considerations. But there's some research showing that if your spectrogram is sufficiently coarse-grained, it's not possible to recover the speech anymore. So you can't hear what people are saying. So then you're doing better for privacy. Audio embeddings, I haven't talked about it, so I won't, but there's a way to compress a learned representation using a CNN, for example, of say 1 second of sound, and you can get just a point in a space. So it's hard to, you can't understand it as a human anymore, but it has somehow the relevant information. So it's possible to do. That's research level stuff so far. Or you can move the entire classification onto the sensor and only send out the, let's say, the decision or the prediction that was made. That is the one that costs the least in terms of data transmission. However, it does cost more in data processing on your sensor. But this balance generally is in favor of, or can often be in favor of, lower power usage. And especially with neural network accelerators, that balance will shift dramatically. So that's our kind of, and with sound sensing, we can use a combination. We can do this part, and we can also do a spectrogram with low resolution to avoid privacy issues. So if we look at our kind of our platform, we have applications at the top, so who might be using certain solutions. We are right now working a lot on noise monitoring, so giving acousticians, but also people in the construction industry or offices, information about what noise is going on. And you have models there that can be reused. We're building some of those. What we're focused on so far is a lot on this sensor and data transport. So we provide a sensor, and it transports the data to database, and you can just access that in an API. So that if you know machine learning and HTTP APIs, you don't have to deal with all the, let's say, IoT sensor data transport parts. We will handle it for you. And then we will also provide more of the models up there eventually. And other applications that people are approaching us about is, for example, condition monitoring. So understanding how machines are doing in manufacturing or real estate, ventilation systems and so on, or process industry. So yeah, that's what we provide. And then yeah, we can deploy models. Either we can have models running in the cloud, or we can have them running directly on the sensor device. So here's an example of that. Not so including. So it's classifying in real time, and here's children playing. It's now the main one. The bar there represents this kind of a threshold. So if everything is below that bar, say, I don't know, rather than say, oh, it must be this thing. There's drilling, it's a little bit. Construction type noise. And all the classification is running on the device. So it's just reporting the predictions over USB. Dog barking. I think this one is interesting because that doesn't get picked up. The woo. There was like two different components to the sirens. The first part, the doo-doo-doo-doo, didn't pick up. The second one did. So somehow that part was probably, I haven't checked this data set that we used to train this model, but it's quite likely that that type of siren sound was not represented in that data set. So the model didn't know. It didn't know that this could be a siren. And yeah, and all these things what we put together to build this noise monitoring solution for acousticians, and we are running pilot projects with customers now. Okay, as an outro, we have some calls to actions for you guys. So we are building a kind of partner network. So we see that in many cases, customers want something really, really, really specific, and we would like to keep, our small focus. We are a small team, 3 people in the core, and a bigger, like around 10 people that are around. We need to keep those at, let's say, on the generic parts. So we're interested in partners that are interested in delivering solutions and integrations for particular needs. So the customer says, oh, I want this kind of thing. So then someone can help us with that. So Knowit, and it's quite could be interesting for that. So reach out to me later or by email if that's interesting to you. We are also hiring. We have some internships running in data science now. We still have maybe a spot to there, and we're hiring 2 developers in 2020. So if you think this sounds cool and interesting, then get in touch with me. And we're also fundraising right now. As a startup does, you kind of have to, right? Well, you both have to to be called a startup, but also because we still need some money to fund projects. We're funding round open now. You can talk to Ola, who's sitting there, and we have quite a lot of commitments already, but we still have some open slots. So.
It's closing in now, so it's actually more like 80% commitment.
Okay, so be fast.
So if you have some money burning in your pockets.
Yes, get in touch. Yeah, I have quite a lot of resources on machine hearing and machine learning on audio online. I put as much as I can out there because it's compared to image, text, and so on. It's a smaller field, yes, and it means there's less learning resources. It's a bit harder to get started. So I try to put as much. So these are links you can go to learn a bit more. And my thesis is also available online. So, questions? Yeah.
So, in your sample,
We should use the microphone. Yes.
yeah. I know. So, in your examples, you use very, in my opinion, like simple sound samples, right? That played like it was one major sound that was distinct. This is children playing, or this is a car horn.
Yep.
But are there neural networks or solutions to complex soundscapes? So in everyday city life, as an example,
yep.
I walk down the streets and I can hear children playing, I can hear a dog barking, a car going by, and a siren.
Yep.
Right. And for automotive vehicles and such, understanding sound as like a sound.
Yep.
Like a sound radar would be interesting, right?
Yes.
Is there a solution for this?
Yes, our solution, I don't know, but there's a whole research field and many application. So you would typically model them as a multi-label classification or a tagging task, so often called tagging. Then you will get a, let's say, percentage of probability. It's not the percentage of, so at least for multiple. So you can have like, oh, there's this thing and a little bit of that thing. So reforming as a label task, there's a challenge at DCase, which is a small but significant conference in this area that has that particular use case as this automotive context understanding. So there are a bunch of open source implementations and papers describing their approaches, and it seems to be doing pretty well there. Also in this data set that we have here, there are also sounds that are far in the background. It's still just annotated with one sound, but there are definitely tricky ones. And that's why humans even can't get to the top. It's like, hey, there's some sound there, it could be. And then it's in 5 seconds, 10 or 4 second intervals, so often sometimes you can't precisely determine what it is. So definitely you can go that far, and things are moving in that direction. More questions? Nice.
So you say as there's a lot of research on using images or cameras for classification, but not as much on audio. Do you think audio classification can match the performance of image classification?
Yeah, I mean it is. So image classification reached, these estimates, but reached kind of human level performance around like 5 years ago. Yep. Or so. And audio, depending on the time, I mean, it's not always, like for example, in speech, we're not near human level yet. And we have been trying since the 70s to get there. And so it's been a big bump with the deep learning, but still not. So, but many practical tasks, it seems that, yeah, we are at close to human level performance on audio tasks. But like speech and music understanding is really, can be really complex. What people expect.
Thanks.
More questions? Yeah. Way back.
Throw it.
Nice.
Thanks.
Have you tried to use more than one microphone to do classification?
I haven't personally tried that, but this is a lot of research. Actually, that's a good point. It's another, let's say, technology wave. So for example, an Alexa now has 8 or 16 microphones in an array, and it can actually use multiple microphones to, you can both do classification with all these microphones, but also you can actually get a cone of sound. So if you have noise source there and this interesting thing there, you can actually focus to a level that sound in that direction, and then you run your classification on that. And again, the DCase conference has, I think now 2 years in a row, a case where they have microphone arrays, I think 5 of them in a home, and like each have 16 sensors or something like that. So that's definitely very active research, and it's gonna be in home or like in challenging applications, like for example automotive as well. I'm almost willing to bet that they are not looking at single microphone solutions. They're looking at clusters of arrays, so like 8 microphones here, 16 microphones there, because they're so cheap these days. So yeah, there's methods specifically for that, and then beamforming is this concept where you get a single channel audio from a multi-channel array of sensors.
Thanks.
More questions? There's one down there and one here.
So that makes me wonder about another area of research, which is using multiple microphones for triangulation or like precise direction and speed vector measurement, if there's any research, if you know about any research and the status of that.
There I have found less, but we are very, very, very interested in that because it fits our sensor network model very well. So there are some approaches, but we have actually one pilot project where that's very relevant, and we actually for that one we will have a master's thesis. I hope. I mean, because I haven't seen enough research on this. Next spring is planned. So if anyone's interested in researching that, come talk to us, and we can.
Wouldn't that be more sort of traditional DSP work?
It's a question where you put your, let's say, put the boundaries. So say we have maybe outdoors or a room like this. We have a couple of sensors in different locations, and we're interested in here knowing not just there was speech here, but where there was speech from. Then you can split this into, let's say, one part that does finding, that does the triangulation and so on in a DSP technique. This has been studied for a long time. Yeah. You can do that, and then you do classification. Or you can treat this as a joint task, where you give a network or 2 networks working together. You say, learn, please, both localization and classification at the same time, because there's information from the local thing that helps you, but also information from the classification. So the speech has a certain, let's say, register and might have certain propagation patterns in space, because it's certain tones and so on, and that might reflect more or less and so on. So there's information. If you know that it's speech, you can do better on localization. If you know where it is, you can do better on the classification. So jointly training that should be, and there is research showing that it is possible to get higher. So that's the research motivation for that.
Just a comment. I know that in 2011 there was a company working on a sniper positioning system that uses both beamforming and triangulation for detecting snipers. Yeah. And yeah, it's a Kongsberg-based firm, so you could Google it.
If they're still around, then
I'm not sure if they still operate.
If they're not, there might be some research that we can find. There's also something called Shot Spotter in the US, and some cities have this deployment where they localize gun sounds in a urban environment. At least they say they can do it.
And I have another question. Have you looked into doing classification on the frequencies that we can't hear?
No, not me, but for example, eco-ecology bats are beyond our hearable range, so that's researched quite a lot there. So I'm not sure what the status is, but I don't see, like, it's probably, I mean, it's probably not very different from the thing. Actually, I was contacted by someone interested in radar as well, which is really high frequencies in the gigahertz range. And they said that, yeah, we think that audio type approaches can work here. They have also a spectrogram, which has a very different frequency range, but still shows patterns in the time frequency domain. And sonar, I guess, is also something that in military applications probably is being researched. Any more questions, or are we done? Okay, we're done. Thank you.
Yeah. Thank you, John. Thank you. Yeah, I think that's everything. Thanks to John, Mikkel, and Evan, and Per. And yeah, that's it. Thank you.